Howdy, everyone. I hope you had a nice mini spring break. Uh, I hope you didn't go to Florida and get into that crazy situation out there. Uh, this cartoon, I think, is interesting. It shows us that rules that we might learn don't always work, and that's certainly true for quantum mechanics. We have a lot of instinctive beliefs from elementary physics. But when we get down to the atomic and molecular level, these things often fail. Okay, where we stopped last time, we're talking about uh, vibrations of polyatomic molecules, and we looked at this molecule here in the spectra. I try to emphasize the difference between infrared and Raman spectroscopy. In infrared spectroscopy, you want to have a large dipole moment change. So here's a carbonyl stretching this strong. In Raman spectroscopy, you want to have the shape of the molecule change quite a lot. So here's the carbon-carbon double bond uh, stretching. This has very little dipole moment change, so it's very weak in the infrared, but you can pick it up in the Raman. So I think this molecule is a good example of how you utilize both kinds of spectroscopy to learn about vibrations. Then I showed you a PowerPoint slide which basically showed all of these vibrations. Our grader Dallas Freitas has said he's now put this on eCampus, so you can look at these again if you wish. And this afternoon I was going to show you a couple other molecules. Last year I had a bunch of students do calculations of molecules for an honor section of PChem. And so I'm going to share some vibrations of some other molecules at this time right now so you can see what vibrations of polyatomic molecules look like. So I'll stop the share and I will share the screen again. And let's do this one. This is trans-butadiene, so John Jung looked at this molecule, and here is his slide presentation. Butadiene, of course, is typically a molecule very important for many chemical engineers. It's used in making, as it says here, golf balls, rubber tires, things like that. So he went through symmetry rules for this. He calculated what the infrared and Raman spectra would look like. You can see they're quite different. Here's a very strong carbon-carbon double bond for this molecule, and other vibrations are in the infrared spectrum. Okay, so here are some of the motions that are taking place. Now, the things that I want you to pick up on, notice that there are 4 equivalent symmetry-wise hydrogens at the N carbons, so these CH2 groups. So these 4 hydrogens are equivalent, and so anytime one of them moves, the other ones have to move at the same time. So this one would be called an anti-symmetric stretch out of phase. At both carbons, one bond is getting longer, and one is getting shorter. Okay, here's again another anti-symmetric stretch. You can see one is in phase and one is out of phase when they're doing. Here's the symmetric stretch. The CH2 groups are stretching at the same time. But notice that the frequencies change. These two are almost identical. You can see they only change in the 10th of the wave number. This one is about 75, I guess. Wave number is lower. All right, here's another CH stretch, but notice this is primarily these central carbon stretches. So even though there are a total of 6 carbon-hydrogen bonds, you will see 6 independent vibrations. And even if you have equivalent atoms, they give rise to different frequencies. And that's the last of the CH stretches that you have. So any organic molecule you're going to be looking at, you should see CH stretches. In this case, all the carbons are conjugated, so all of these frequencies are quite a lot higher. In alkanes, the frequencies are typically more like 2,900 wave numbers, a couple hundred wave numbers lower. Okay, so all 6 CH stretches. All right, this one involves the stretching of these double bonds, and notice that they're equivalent, and so they have to vibrate together. As I pointed out last time, we're greatly exaggerating these motions. The motions typically only involve change in about 10% of the bond distance. Here it looks like it would be 100%. Okay, so both of these are carbon-carbon double bond stretches that you see. This one is called the scissors motion, or the Ch2 motion. As I pointed out last time, spectroscopists get very descriptive, so this nicely looks like a pair of scissors. And these two on the end are in phase with each other. Here's another scissors motion. Well, in fact, this is the one that's in phase. The other one is apparently out of phase. These are wags of mostly of the central atoms. But again, notice that much of the rest of the molecule wobbles too. So there's a lot of so-called coupling between the different motions. And this is another bending motion. That's the carbon-carbon single bond stretch. It's actually a partial double bond. As you get lower and lower, you get more bending motions. You can see these NCH2 groups are twisting a little bit, and then this CH is wagging up and down. These are called rockings. It's kind of a sideways rock. If you straighten the molecule up, then you could picture this as a rocking chair going up and down. This is an out-of-plane CH bend for these motions. These are out-of-plane wags of the CH2 groups. And another wag. More rockings, more twistings. Anyway, we don't need to belabor this, but I just want to give you an idea of what kind of motions you actually are getting. Notice this one is mostly a carbon-carbon-carbon angle bending. So this angle right here and that angle right there are bending. And this might be the lowest vibration. It's kind of bending around the middle. Well, one more, torsion. Okay, this is totally out of plane. It's basically trying to rotate around the single bond. I think I said that, but Dallas put the vibrations that I showed you last time on eCampus, if you want to look at them. He also put this molecule there. You can see that you can have a lot of fun with motions that John did for this one. Okay, I'll stop share again, and I'll show you yet one more molecule, if I can find it. Okay. These are calculations that James Corbin did last semester. And this is for 1,4-difluorobenzene. Calculated infrared spectrum, calculated Raman spectrum, and his frequencies, he lists them from high to low. So again, the low ones are mostly going to be wags, out of plane motions, things like that. The bluish colors are the fluorine atoms, and then we recognize the darker carbons and the hydrogens here. Again, the low motions, there's just kind of lots of wobbles and wags and twists when you look at these molecules. This would be an in-plane wag, mostly of the fluorine atoms right here. The rest of the molecule is moving because you can't incorporate translational motion into a vibration. So we have to try to keep the center of gravity fixed and also not generate any rotational motion when these calculations are made. Okay, we're working our way up in frequency, but these are still all bending motions. This is now a bending of the entire benzene ring that you can see. There's a twisting of about every other carbon-carbon bond. So this goes up, this goes down, this goes up, this goes down, so on. All right, this would be a CH WAG. Those are at higher frequency than the fluorines because they're lighter atoms doing the vibrations. And that's similar, but here the motions are together. Again, notice that the 4 equivalent hydrogen atoms are moving all at the same time. So you don't get individual motions and have them all be at the same frequency. You get 4 combinations of these kind of motions. Okay, every benzene ring has this vibration, which is one of the strongest vibrations in Raman spectra that you can get. This is called the ring breathing again. We looked at that last time. So it looks kind of like a lung opening up. But what you see is every carbon-carbon bond is stretching, and so you can call it a ring breathing. This is mostly a stretching of these bonds. It looks like these CHs are moving, but it's most of the forces and energy goes into having these 2 bonds contract and these 2 expand. Getting this again is mostly carbon fluorine stretching. So this bond is stretching while this one is getting shorter. So it'd be called an anti-symmetric carbon fluorine stretching. This would be the symmetric stretching that you can have. And you can see the benzene ring is also crazily participating as we do this. So as the fluorines pull out, the benzenes have to move in to maintain the center of gravity. Greatly exaggerated anti-symmetric in-plane motion of the carbon-carbon bonds stretching or compressing. Here we're now up to the last 4 vibrations, the CH stretches that we have. So there'll be 4 of these involving these 4 carbon-hydrogen bonding. This is another one. This is another one. This is more symmetric. And then I think this is the last one. Okay, so I just want to give you more ideas, more of an idea of what to expect from these things. Okay, someone asks if these PowerPoints will be tested. Yes, I will ask you to draw a picture of every one of the vibrations I showed you. No, I just want you to pick up general features of what there are. I might mention the exam, which is a week from today. We'll review for this on Wednesday. It will cover the concepts through what we're discussing today. So only through vibrational spectroscopy. We will not get into electronic spectroscopy on the examination. And as far as polyatomic molecules go, I could ask you some concept questions. Incidentally, the exam is going to have 40 points of true and false. So make sure you understand the concepts. Some of the true and false will be pretty trivial and easy, and you can get them out of your notes. Others you're going to have to think about and apply some of the concepts that are in the notes. Okay, we'll stop share again, go back to share screen again, and see where we were. Okay, so I've now shown you 3 polyatomic molecules and what the vibrations look like. Here's just another example that I wanted to show you of spectra. and vibrations. This is the ammonia molecule, and these are symmetry designations. And when we have a capital E, it means there are two vibrations of the same symmetry. So a polyatomic molecule has 3n-6 vibrations, and that's the kind of concept question I could ask you. So with 4 atoms, it has 6 vibrations. What's labeled nu1 here is 1 vibration, nu2 is another one. Nu3 actually represents 2 vibrations. There's 2 ways to have the anti-symmetric stretch. They both occur at the same frequency, 3414. So we are only going to have 4 frequencies, even though we have 6 vibrations. The same thing for an angle bending. There's 2 ways that you can combine the angle bendings that you have in ammonia. A couple of features I wanted to point out here, the symmetric and anti-symmetric stretches of ammonia. You can see they're actually pretty weak. The first and third vibrations are there. This is the angle bending motion. And then this is what's called the inversion. And I'll say a little bit more about that. But notice there's rotational fine structure on the sides of these vibrations. So I mentioned to you last week that when you have molecules like methane, for example, you cannot study their rotational spectra either by infrared or Raman spectroscopy. But when you go to looking at the vibrations, you can look at the combinations of vibrational rotational spectra and pick up rotational features. So if we analyze this rotational structure on these bands for ammonia, we could figure out what the rotational constants would be, for example. I'm also showing you this spectrum to point out that spectroscopy can really get to be quite intriguing and complicated. You'll see there are 2 bands here for nu2. The nu2 vibration is the inversion. So ammonia has kind of a pyramid structure, and it can flip over so that this umbrella-like shape goes in the opposite direction. To do that, it has to go through a flat planar structure. And whenever you have a situation like this, you have what's called inversion doubling. And so you see 2 bands actually showing up here. And if we analyze the spectrum very carefully, we could calculate the energy difference between a planar ammonia molecule and what one of these umbrella-like more lower energy structures are. So there's a lot of fun things you can do with spectroscopy, and so that's just kind of something I wanted to show you. Okay, the very last thing I want to tell you about polyatomic molecules is that many organic molecules have either CH2 groups or CH3 groups or CH groups, and you can go to books and you can find what to expect for these vibrations. In your notes, I included the symmetry aspects of how to look at these vibrations, but basically here I want to just give you pictures of what the vibrations are of a CH2 group. So I'm taking basically a C3H2 structure, so that's 5 atoms, and we can look at 9 vibrations that you would have. So if you go out in industry and you work in a lab where people might be taking infrared spectra of some of the molecules that you're working with, it's going to be very common that you're going to have the CH2 vibrations to look at. So as I said, this is just kind of to give you a little bit of a head start on knowing what to see in the spectrum. All right, so I've labeled these from high frequency to low frequency, and I've labeled them according to symmetry. So the first vibrations are the most symmetry. This is called the symmetric stretch. The 2 bonds are stretching out at the same time, very similar to the OH symmetric stretch that we had in water. This is called a scissors, and you can see why. Actually, in journal articles, it's typically called a CH2 deformation. This is at about 1450 wave numbers. This is about 2900 wave numbers. In this system that I'm showing you, I also have two carbon-carbon bonds. So you'd have a carbon-carbon symmetric stretch. Carbon-carbon bonds vibrate at around 900 wave numbers. And finally, the lowest vibration of this highest symmetry is a carbon-carbon angle bending. So stretches are always highest in frequency. Light atoms have the highest frequencies, and bendings have the lowest frequencies. This one's called a twist, and you can see why. The upper hydrogen atom is moving out while the lower atom is moving in. So it's going back and forth like that. This one's called a wag, and you can visualize that if this were a dog with two tails, it would be wagging back and forth like that. We have another chat question. Someone asks if there's a way I could email out the practice problems, again, as a PDF. That was helpful, having them outside of the course pack. I will see if I can do that. It's not always easy for me on my home computer to manipulate things like that, but I will try to do that. Okay, then we go to less symmetric cases. This is a CH2 twist that we have. Again, one coming forward, one going back. This one says CH2 wag. I guess I just did those, sorry. Here I left out the frequency, the CC2 anti-symmetric stretch. This might be 2970 wave numbers. Anti-symmetric, oh, sorry. I'm making a lot of mistakes. This is carbon-carbon anti-symmetric stretch. So this would be about 1,000 wave numbers because it involves carbon-carbon single bond stretches that we have here. Then finally here we're back to the CH2 stretches again. The anti-symmetric stretches tend to be higher than symmetric stretches. So this is about 2950. And finally, we have the Ch2 Rock, which is always lowest. So a Ch2 group always will have 6 vibrations: a symmetric stretch, an anti-symmetric stretch, a twist, a wag, a deformation, which is also called a scissors, and a rock. And if you have a large molecule, like say octane, it's going to have lots and lots of these Ch2 groups. And every one of those groups will interact with the other Ch2 groups to give you a lot of vibrations in these particular ranges. So if you have 4 Ch2 groups, you're going to have 4 Ch2 wags, and some will be in phase with each other and so on. So that's what tends to complicate infrared spectrum. Just a couple of applications. I want to show you utility of vibrational spectroscopy. Here's a Raman spectrum, and it's called a resonance Raman spectrum. What resonance means is that they're using a laser that's close in frequency to exciting an electronic band. And when you do that, you can enhance a lot of the intensity of these vibrations that you're looking at. Anyway, this is chlorophyll. This is done at 30 degrees Kelvin, simply so that makes the bandwidths smaller. You can look at them. And on top of each one, you can see there's a description. When it says nu CN, it means it's mostly a vibration of a carbon-nitrogen stretch. Here we're at around 1600. This is carbon-carbon stretch. When we have deltas, that means they're bending. This is carbon-nitrogen-carbon bond bending and so on. So detailed analyses of important molecules can be done. Raman spectroscopy has a lot of advantages over infrared because water doesn't interfere. So you can look at biological systems in water, and water doesn't wipe out the spectrum by water absorption. Another chat comment. The answer is yes, there are always 6 CH2 vibrations. So in what I showed you, I also showed you carbon-carbon stretches. So I showed you 9 vibrations because I included 2 carbon-carbon stretches, and then a carbon-carbon-carbon bending. But every CH2 group has 6 vibrations. Every CH3 group has 9 vibrations. Every CH group has 3 vibrations. That's more detail than I want to pass on to you. I mean, you're not responsible for knowing all that. If you ever need it, there are lots of books in the library that you can look at. So in this picture, yes, I said that delta represents bending motions. When you have a nu, that means it's a stretching. If you have deltas, it's some kind of bending motion. Then here's another example of a practical application. This was done at Triangle Park, North Carolina, where they do a lot of work for the Environmental Protection Agency. So what the people did here was they took air and they froze it down to very low temperature. So they condensed many, many molecules out of the air and concentrated them. And then they put them into a long path cell where you could get a lot of intensity from your samples. Then they could see what was actually in the air. And if you look here, there's a lot of what are called chlorofluorocarbons. And this was a big problem before most of you were born. The Freon cooling agent that was in refrigerators and air conditioners, it contained chlorofluorocarbons. They needed to be non-ideal gases, and they were perfect for that. Unfortunately, they were also perfect for attacking ozone. And as you probably know, we rely on the ozone layer that we have in the atmosphere to wipe out a lot of the ultraviolet light that would be getting down here to Earth. So again, 30, 40 years ago, it was decreed that you couldn't use these anymore. We now have less efficient cooling agents, but we have a lot better atmosphere, and we don't have to worry so much about getting sunburned. Okay, our next topic, and this will not be on the exam next week. Our next topic is going to be electronic spectroscopy. And I'll come back to this diagram and tell you about that. But I wanted to jump ahead and tell you about molecules in space that have been detected by vibrational spectroscopy. You'll remember during our discussion of Hückel treatments, I showed you that we expected H3 neutral to be a more stable molecule when it was triangular as opposed to linear. So that just came out from the regular Hückel type calculation. But in that diagram, I also showed you that H3 plus would be even more stable because the third electron that you would have in neutral H3 would go into an antibonding orbital. So this has now been made on Earth, and it's been confirmed that it's all over the universe, all over the place. And why it exists out there is it takes so very long before any of these molecules collide with anything else. So every H3 molecule might go 5 years before it ever smashes into something else. And then it might become H2 or H atoms or whatever. But here's a listing of some of the molecules that have been looked at in space. I just picked some atoms 10 to 70. Just about all the small atoms, all the small molecules with less than 10 atoms have been looked at. The CN diatomic molecule is very useful for telling us what the temperature is, whether it's in outer space or anywhere else. But all of these other molecules have been looked at also. You can see even these so-called fullerenes, which are also called buckyballs and get up to mass of 840. Those have been detected out in space. Okay, well, let's go back to this diagram. And so this is kind of a preliminary look at what we're going to deal with in electronic spectroscopy. Mostly we'll look at polyatomic molecules, but in every case, we're going to look at electrons jumping from one of the molecular orbitals in the molecule and going to a higher orbital, typically, which is antibonding. In the case of bromine, I think you all drew Lewis-Rot structures of molecules like this. You would draw a single bond between two bromine atoms and then put 6 non-bonded electrons around each bromine atom. Okay, there's a question. Is the molecules in space on exam 2 or 3 topic? I don't think we talked enough about it that I would ask you a question on it. But you would have access to your notes anyway, so if I asked you to name a molecule in space, all you'd have to do is go back to that table that I showed you. That would be there. Vibrational spectroscopy will be on the second exam, so in principle, molecules in space could be on the exam. I could ask you some general true or false question or something. Okay, anyway, you remember when we talked about diatomic molecules, we drew a curve like this. If we push the 2 bromine atoms together, then the potential energy goes to infinity as the nuclei get very close together. As we pull the 2 atoms apart, we hit a dissociation point. So at this dotted line, the 2 bromine atoms would fall apart and we'd have 2 individual atoms. So go back in your notes and make sure you understand our discussion of diatomic molecules. When we discussed that, I also showed you what the quantum states were for vibrations. For bromine here, they're so very close together, only every other quantum state is shown. So there's B equal to 0, 2, 4, 6, 8, and so on. But the odd ones also exist. B equal to 1 exists, B equal to 3. So you can see these are pretty closely spaced, kind of like the harmonic oscillator model. But if we went further up, they would start getting closer and closer together. Again, the dissociation energy for bromine would be from the bottom of this curve up to the dotted line. The actual energy that it would take would be from where the 0 is, because that's the 0-point energy, up to the dotted line. What this diagram shows is if we take a non-bonded electron in bromine and we excite it to an antibonding orbital, our bond order goes from a single bond down to a half bond. And so this is what the potential curve looks like for the molecule in the electronic excited state. So first of all, that excited state, you can see, is about 16,000 wave numbers higher than the ground state. That's about the amount of energy it takes to take that electron from a non-bonded orbital into an upper state. I'll show you more specific examples later of those molecular orbital transitions, but this is essentially what we're talking about, going from one molecular orbital to another. When we're in the excited state, I like to think of this as a totally new molecule. It's still Br2, but it only has a bond order of 1/2 because of that antibonding electron up above. And we still have 2 bonding electrons that we had before. So 2 minus 1, take half of that, gives you a half bond order. When you're in this excited state, the bond is very much weaker, and the dissociation energy is from the bottom of this curve up to the second dotted line. And so you can see that's only about 4,000 wave numbers. This gives you a good example of how photochemistry works. If you excite the bromine diatomic molecule into its excited state, it can very easily dissociate because it only takes 4,000 wave numbers to break the bond apart. I don't know what kind of reactions you ran in organic chemistry lab, But when I was in college, we did an experiment making bromobenzene from bromine gas, bubbling it into benzene, taking a cheap Walmart light and exciting the bromine molecule, and voila, we had bromobenzene. And that occurred because we got bromine into this excited state. We'd have the diatomic molecule split apart into atomic bromine. The atomic bromine would attach itself to the benzene, kicking off a hydrogen, and I guess we'd get HBr bubbled off. But keep this in mind always now when we talk about electronic excited states. They're typically going to have weaker bonds, and they're going to be at higher energies. The other thing to notice, at the bottom here, this is the bond distance. So the bromine-bromine bond in the diatomic molecule is about 2.3 angstroms. But up here, you can see this is something like 2.7 angstroms. So when the bond order goes from 1 to a half, the bond gets weaker and longer. Okay, so that's just kind of a preliminary introduction to electronic spectroscopy. So I like to say this over and over again. The world is beautiful because of electronic spectroscopy. Every color you look at comes from electrons jumping from molecules, from molecular orbitals to higher molecular orbitals, or possibly from atoms to higher energy orbitals. I also like to point out, and maybe I'll tell you about this next week or so, we wouldn't have life if we didn't have electronic transitions. So we couldn't have photosynthesis without electronic transitions. We didn't have photosynthesis, we wouldn't have plants. We didn't have plants, we wouldn't have animals, and we wouldn't be around either. So this is a very important aspect of life in general. Okay, so this is the beauty part. Colors of all materials are due to the absorption of some frequency of light for electronic transitions. The visible region that we look at goes from about 370 nanometers to 700 nanometers. If we go to longer wavelengths, we get into the infrared region. If we go to higher energies and lower wavelengths, we go to the ultraviolet. Within the visible range, the violet is the highest frequency light that we can see, and red is the lowest frequency light that we can see. And you can see then why this would be called infrared and this region is called ultraviolet. Okay, so just so we're thinking alike, let's say this is a spectrum, an absorption spectrum of some material. And if we're looking at it, if it absorbs here and here, but doesn't absorb blue and red, then what we're going to see is the blue and red being reflected. So think of this again as maybe, I don't know what if blue and red together quite makes algae maroon or not, but think as blue and red not being absorbed by the dye that you have, but being reflected, but greens and yellows and other colors are being absorbed. This is what color is that you would see in the universe. And we have a chat comment. No, electronic spectroscopy is not on the exam. So all of this is new material, but we are still going to continue and talk about it a little bit. Another question? I guess that was it. Okay, I didn't set up showing you the absorption spectrum of chlorophyll, and rather than waste your time by my looking at it, I just wanted to point out here, this is roughly what the absorption spectrum of chlorophyll looks like. It absorbs light in the red or blue regions, but it does not absorb light in the green region. So this is why plants are green. Many of you at some point are going to get married and have kids, and your kids are going to have to do junior high science projects. I've suggested this to quite a few students over the years, and quite a few students have written back to me and said, yes, they had their kids do this project for a science fair, and in some cases, they've actually even won the science fairs. A project you can do is try growing plants under different colors of light. You can just get some transparent paper that transmits just blue or yellow or red. And what you'll find is plants will not grow when you only hit them with green light. So chlorophyll doesn't like green light. It doesn't get itself excited. It can't go through photosynthesis. But if plants get blue light or red light, they can absorb and get into excited states and have reactions take place. So jot that down on your iPhone to remind you in 10 years or so to choose that for a project for your kids, whatever. Okay, so I hope I've made that clear, but when you see a color, what you're getting, what you're seeing, that's the color that's being rejected. So plants don't like green, so they just bounce it off, they reflect it, they absorb other colors, and those other colors are useful for growing and so on. The next thing I've stuck into your notes, and it doesn't really belong in electronic spectroscopy any more than it did in vibrational spectroscopy, but especially chemical engineers, I think, do not take an analytical chemistry course. You may have run into the Beer-Lambert law in freshman chemistry when you did some quantitative measurements, but I stuck it here anyway so you can get some sense of how you can do analytical spectroscopy with either visible light or ultraviolet light or infrared light. Basically, the idea is if you have a sample and you shine light in of initial intensity I0 at some frequency nu, you have a sample of path length L, and then some light comes out of intensity I at nu. Now, assuming some of the light gets absorbed, then the percent transmittance will be the intensity coming out divided by the intensity going in times 100. So that's called percent transmittance. When you make quantitative measurements, what you want is something called absorbance. And you can show the absorbance is equal to the negative logarithm of the transmittance. And you can further show that this absorbance is equal to something called the molar absorption coefficient times what basically is the number of molecules that you're looking at. So in my example here, I have a path length L. The longer it is, the more molecules I'll have in the path. And then if this is like a liquid solution, then the concentration, if it's high, it would give you more molecules. So absorbance then is the product of the number of molecules times this molar absorption coefficient. And I want to point out here that the molar absorption coefficient is again related to the transition moment integral that we've talked about many times before. Our selection rules came from this, our intensities came from this, but this now applies also to electronic spectroscopy. It doesn't have to be vapor phase. And so many quantitative measurements can be made like this. So just to jump off a page, this is typically what's done when someone may be wanting to analyze the Mississippi River water for trying to see how much chloroform is in it, for example. You create yourself a working curve of taking known concentrations, measure the absorbance, you make the curve, and then when you do an unknown, you just see what the absorbance is, and you read off the concentration as to what comes off. In between those two slides, I have this table. And the bottom line is electronic spectroscopy is not all that great for identifying molecules. However, it's quite well known where certain kinds of systems absorb. So an ether will typically have maximum at 185 nanometers. These are all in nanometers. This is the molar absorptivity coefficient that you can have. And so there's a listing of these types of things that you can find. There'll be, again, big fat books that you can find to see where you might expect absorption. And for certain kinds of analytical studies, if you know you're not going to have interference from something else that absorbs in the same region of the spectrum, then this can be pretty useful. Anyway, a lot of this kind of stuff is known. For qualitative analyses, electronic spectroscopy is not too great, not nearly as good as infrared spectroscopy or NMR spectroscopy, for example. Okay, well, we've just got a little bit of time left, and so just to help get us started on what we might expect in electronic spectroscopy, I've taken a carbonyl group that might be in a ketone or an aldehyde and shown you what the bonds are. So you'll see the carbon-oxygen bond is a double bond. So one of the bonds will be a sigma type orbital, one will be a pi type orbital. So think back to our discussion of when we talked about carbon monoxide, for example, or N2. We had a sigma bond and we had a pi bond. And in each case, we also had an antibonding orbital, so a sigma star and a pi star. A carbonyl group, this is the way you draw the Lewis structure, it also would have had 4 non-bonded electrons in 2 of these non-bonded orbitals, mostly p orbitals that you would have. So if we wanted to draw a qualitative molecular orbital energy diagram for this, this is what we'd have, sigma pi and pi star sigma star. So we have 4 electrons in the carbon-oxygen bond and then 4 more non-bonded electrons. This is what the diagram would look like. If we want to do electronic spectroscopy on a ketone or aldehyde, then in principle, any one of these transitions can occur. We can go sigma to sigma star, pi to pi star, n to pi star, n to sigma star, and these are approximately where they would occur. Remember that vibrational spectra occur mostly between about 200 and 4,000 wave numbers. We're now about 10 times higher in energy for these electronic transitions. We're going to see that there are certain selection rules for saying which of these transitions we expect to be more likely, but in principle, all of these can be looked at. And in all of these cases, we're going to have, again, our delta E is equal to H nu. Hate to do this to you, but we have 2 minutes left, so I'll tell you about one more thing. We're going to have a selection rule that says when electrons jump from one orbital to another, the spin of that electron can't change. So this is normally what would happen if I have a pi to pi star transition. I can take an electron here, shine it up about 50,000 wave numbers, and the electron in the upper orbital is going to still be opposite in spin to the lower one. So this system would not be paramagnetic. It would not have any unpaired electron spin. And so this is the only state, the only electronic state that you can form directly. And this is going to be called a singlet state. However, we're going to find that this other state can exist and it can be formed, maybe not as directly as an absorption, but in this case, the electrons wind up spinning in the same direction. And there are going to be 3 quantum mechanical ways that we can represent this upper state. So this is going to be called a triplet. But this gets to be very complicated. We've conveniently run out of time. Wednesday, we will have a review for the exam. Friday, I want to tell you about glaciers melting and global warming. Next Monday, we'll have our exam. So we won't get back to worrying about the singlet and triplet states until a week from Wednesday, it looks like. Another chat comment. The third time I've been asked, electronic spectroscopy is not in the second exam. Correct. Okay, so tune in Wednesday. We will have a review. I've sent you a review. And let me emphasize, you'll want to be looking at practice problems that are in the lecture notes on diatomic molecule vibrations and rotations, also on Hückel problems and on Aufbau type problems for homonuclear diatomics. And if you tuned in late, our second exam is going to have 40 points in true and false. So make sure you understand the concepts. Okay, take care, stay healthy.